1.2.4. Finding domains and ranges of the toolkit functions. We will now return to our set of toolkit functions to determine the domain and range of each. Figure 13. X, f of x. F of x equals c. Domain. Open parenthesis, negative infinity, infinity, closed parenthesis. Range. Open square bracket, c, c, closed square bracket. For the constant function f of x equals c, the domain consists of all real numbers. There are no restrictions on the input. The only output value is the constant c, so the range is the set C that contains this single element. In interval notation, this is written as open square bracket, C, C, closed square bracket, the interval that both begins and ends with C. Figure 14. X, f of x. Domain. Open parenthesis, negative infinity, infinity, closed parenthesis. Range. Open parenthesis, negative infinity, infinity, closed parenthesis. For the identity function f of x equals x, there is no restriction on x. Both the domain and range are the set of all real numbers. Figure 15. X, f of x. Domain. Open parenthesis, negative infinity, infinity, closed parenthesis. Range. Open square bracket, 0, infinity, closed parenthesis. For the absolute value function, f of x equals the absolute value of x, there is no restriction on x. However, because absolute value is defined as a distance from 0, the output can only be greater than or equal to 0. Figure 16. X, f of x. Domain. Open parenthesis, negative infinity, infinity, closed parenthesis. Range. Open square bracket, 0, infinity, closed parenthesis. For the quadratic function, f of x equals x squared, the domain is all real numbers since the horizontal extent of the graph is the whole real number line. Because the graph does not include any negative values for the range is only non-negative real numbers. Figure 17. X, f of x. Domain. Open parenthesis, negative infinity, infinity, closed parenthesis. Range. Open parenthesis, negative infinity, infinity, closed parenthesis. For the cubic function, f of x equals x cubed, the domain is all real numbers because the horizontal extent of the graph is the whole real number line. The same applies to the vertical extent of the graph, so the domain and range include all real numbers. Figure 18. X, f of x. Domain. Open parenthesis, negative infinity, 0, closed parenthesis, union, open parenthesis, 0, infinity, closed parenthesis. Range. Open parenthesis, negative infinity, 0, closed parenthesis, union, open parenthesis, 0, infinity, closed parenthesis. For the reciprocal function, f of x equals 1 over x, we cannot divide by 0, so we must exclude 0 from the domain. Further, 1 divided by any value can never be 0, so the range also will not include 0. In set builder notation, we could also write the set of x values such that x is not equal to 0, the set of all real numbers that are not 0. Figure 19. X, f of x. Domain. Open parenthesis, negative infinity, 0, closed parenthesis, union, open parenthesis, 0, infinity, closed parenthesis. Range. Open parenthesis, 0, infinity, closed parenthesis. For the reciprocal squared function, f of x equals 1 over x squared, we cannot divide by 0, so we must exclude 0 from the domain. There is also no x that can give an output of 0, so 0 is excluded from the range as well. Note that the output of this function is always positive due to the square in the denominator, so the range includes only positive numbers. Figure 20. X, f of x. Domain. Open square bracket, 0, infinity, closed parenthesis. Range. Open square bracket, 0, infinity, closed parenthesis. For the square root function, f of x equals square root of x, we cannot take the square root of a negative real number, so the domain must be 0 or greater. The range also excludes negative numbers because the square root of a positive number x is defined to be positive, even though the square of the negative number, negative square root of x, also gives us x. Figure 21. X, f of x. Domain. Open parenthesis, negative infinity, infinity, closed parenthesis. Range. Open parenthesis, negative infinity, infinity, closed parenthesis. For the cube root function, f of x equals the cube root of x, the domain and range include all real numbers. Note that there is no problem taking a cube root, or any odd integer root, of a negative number, and the resulting output is negative. It is an odd function. How to? Given the formula for a function, determine the domain and range. 1. Exclude from the domain any input values that result in division by 0. 2. Exclude from the domain any input values that have non-real or undefined number outputs. 3. Use the valid input values to determine the range of the output values. 4. Look at the function graph and table values to confirm the actual function behavior. Example 8. Finding the domain and range using toolkit functions. Find the domain and range of f of x equals 2x cubed minus x. Solution. There are no restrictions on the domain, as any real number may be cubed and then subtracted from the result. The domain is, open parenthesis, negative infinity, infinity, closed parenthesis, and the range is also, open parenthesis, negative infinity, infinity, closed parenthesis. Example 9. Finding the domain and range. Find the domain and range of f of x equals 2 over x plus 1. Solution. We cannot evaluate the function at -1 because division by 0 is undefined. The domain is, open parenthesis, negative infinity, -1, closed parenthesis, union, open parenthesis, -1, infinity, closed parenthesis. Because the function is never 0, we exclude 0 from the range. The range is, open parenthesis, negative infinity, 0, closed parenthesis, union, open parenthesis, 0, infinity, closed parenthesis. Example 10. Finding the domain and range. Find the domain and range of f of x equals 2 square root of x plus 4. Solution. We cannot take the square root of a negative number, so the value inside the radical must be non-negative. X plus 4 is greater than or equal to 0 when x is greater than or equal to -4. The domain of f of x is, open square bracket, -4, infinity, closed parenthesis. We then find the range. We know that f of -4 equals 0, and the function value increases as x increases without any upper limit. We conclude that the range of f is, open square bracket, 0, infinity, closed parenthesis. A. Analysis. Figure 22 represents the function, f. Figure 22. X, f of x. Triad number 7. Find the domain and range of f of x equals negative square root of 2 minus x. 1.2.5. Graphing piecewise defined functions. Sometimes, we come across a function that requires more than one formula in order to obtain the given output. For example, in the toolkit functions, we introduced the absolute value function f of x equals the absolute value of x. With a domain of all real numbers and a range of values greater than or equal to 0, absolute value can be defined as the magnitude, or modulus, of a real number value regardless of sign. It is the distance from 0 on the number line. All of these definitions require the output to be greater than or equal to 0. If we input 0, or a positive value, the output is the same as the input. F of x equals x if x is greater than or equal to 0. If we input a negative value, the output is the opposite of the input. F of x equals negative x if x is less than 0. Because this requires two different processes or pieces, the absolute value function is an example of a piecewise function. A piecewise function is a function in which more than one formula is used to define the output over different pieces of the domain. We use piecewise functions to describe situations in which a rule or relationship changes as the input value crosses certain boundaries. For example, we often encounter situations in business for which the cost per piece of a certain item is discounted once the number ordered exceeds a certain value. Tax brackets are another real-world example of piecewise functions. For example, consider a simple tax system in which incomes up to $10,000 are taxed at 10%, and any additional income is taxed at 20%. The tax on a total income, S, would be 0.1 S, if S is less than or equal to $10,000, and $1,000, plus 0.2 times, open parenthesis, S, minus $10,000, closed parenthesis, if S is greater than $10,000. A piecewise function. A piecewise function is a function in which more than one formula is used to define the output. Each formula has its own domain, and the domain of the function is the union of all these smaller domains. We notate this idea like this. F of x equals Formula 1, if x is in domain 1. Formula 2, if x is in domain 2. Formula 3, if x is in domain 3. In piecewise notation, the absolute value function is the absolute value of x equals x if x is greater than or equal to 0. Negative x if x is less than 0. How to? Given a piecewise function, write the formula and identify the domain for each interval. 1. Identify the intervals for which different rules apply. 2. Determine formulas that describe how to calculate an output from an input in each interval. 3. Use braces and if statements to write the function. Example 11. Writing a piecewise function. A museum charges $5 per person for a guided tour with a group of 1 to 9 people or a fixed $50 fee for a group of 10 or more people. Write a function relating the number of people, n, to the cost, c. Solution. Two different formulas will be needed. For n values under 10, c equals 5n. For values of n that are 10 or greater, c equals 50. C of n equals 5n if 0 is less than, n is less than 10. 50 if n is greater than or equal to 10. B. Analysis. The function is represented in Figure 23. The graph is a diagonal line from n equals 0 to n equals 10 and a constant after that. In this example, the two formulas agree at the meeting point where n equals 10, but not all piecewise functions have this property. Figure 23. N. C of n. Example 12. Working with a piecewise function. A cell phone company uses the function below to determine the cost, C, in dollars for G, gigabytes of data transfer. C of G equals 25 if 0 is less than, G is less than 2. 25 plus 10, open parenthesis, G, minus 2, closed parenthesis, if G is greater than or equal to 2. Find the cost of using 1.5 gigabytes of data and the cost of using 4 gigabytes of data. Solution. To find the cost of using 1.5 gigabytes of data, C of 1.5, we first look to see which part of the domain our input falls in. Because 1.5 is less than 2, we use the first formula. C of 1.5 equals $25. To find the cost of using 4 gigabytes of data, C of 4, we see that our input of 4 is greater than 2, so we use the second formula. C of 4 equals 25 plus 10, open parenthesis, 4, minus 2, closed parenthesis, equals $45. C. Analysis. The function is represented in figure 24. We can see where the function changes from a constant to a shifted and stretched identity at g equals 2. We plot the graphs for the different formulas on a common set of axes, making sure each formula is applied on its proper domain. Figure 24. G. C of g. How to. Given a piecewise function, sketch a graph. 1. Indicate on the x-axis the boundaries defined by the intervals on each piece of the domain. 2. For each piece of the domain, graph on that interval using the corresponding equation pertaining to that piece. Do not graph two functions over one interval because it would violate the criteria of a function. Example 13. Graphing a piecewise function. Sketch a graph of the function f of x equals x squared if x is less than or equal to 1. 3. If 1 is less than, x is less than or equal to 2. X, if x is greater than 2. Solution. Each of the component functions is from our library of toolkit functions, so we know their shapes. We can imagine graphing each function and then limiting the graph to the indicated domain. At the endpoints of the domain, we draw open circles to indicate where the endpoint is not included because of a less than or greater than inequality. We draw a closed circle where the endpoint is included because of a less than or equal to or greater than or equal to inequality. Figure 25 shows the three components of the piecewise function graphed on separate coordinate systems. Figure 25. A. F of x equals x squared if x is less than or equal to 1. B. F of x equals 3 if 1 is less than, x is less than or equal to 2. C. F of x equals x if x is greater than 2. Now that we have sketched each piece individually, we combine them in the same coordinate plane. See Figure 26. Figure 26. D. Analysis. Note that the graph does pass the vertical line test even at x equals 1 and x equals 2 because the points 1, 3, and 2, 2 are not part of the graph of the function, though 1, 1, and 2, 3 are. Try at number 8. Graph the following piecewise function. F of x equals x cubed if x is less than -1. -2 if -1 is less than, x is less than 4. Square root of x if x is greater than 4. Q and A. Can more than one formula from a piecewise function be applied to a value in the domain? No, each value corresponds to one equation in a piecewise formula. 1.2.6. Media. Access these online resources for additional instruction and practice with domain and range. 1. Domain and range of square root functions. http://openstaxcollege.org/l/domainscroot. 2. Determining domain and range. http://openstaxcollege.org/l/determinadomain. 3. Find domain and range given the graph. http://openstaxcollege.org/l/drgraph. 4. Find domain and range given a table. http://openstaxcollege.org/l/drtable. 5. Find domain and range given points on a coordinate plane. http://openstaxcollege.org/l/drcoordinate.